Okay, so everyone knows this is a short week. All right.
We have a day off.
Yeah, Friday.
Right. Okay, good. So I'm glad everybody now knows. Okay. Yeah, so we only have class Monday and Wednesday this week. Right? Friday, the university has homework. I know it doesn't coincide with the Florida game this year. Yeah. So it's a little strange in that way.
But that game is happening though?
It is. I think it's happening either a week or two. We're playing Kentucky this next weekend. We weren't supposed to. We were supposed to have a bye because of COVID reasons. We're rescheduling in the SEC. Okay. All right. So we're going to continue on with translation functors today. There'll be some technical lemmas that I'll actually state. I won't actually prove them, but I'll show you how these are actually used. And then the output of all this, once we actually find a character formula for the translated module, given the character for the original module, then that'll actually give us a way to prove the categorical equivalence between blocks where the weights are on the same facet. Okay, so let me recall. Let's do a little bit of review. Okay, so last time we had the character formula for the tensor product. So let B be a finite dimensional G module. Okay, with PR lambda B. So all the components are in the same block. All right. So you want to write the character B as the sum of all W and WP of AW pi of W. So you can do this because PR lambda is equal to V, and these Euler characters actually span the entire G invariance for that block. Okay, so the AWs though are in Z, and almost all the AWs are equal to 0. So this is actually a finite sum. Okay, so then the punchline is the character PR nu of any M tensor B. We can write as a formula. This is the WWP of AW. Okay. The sum over nu, dimension M new weight space. And now, of course, we're in the block linked to mu. So this should be, let me just take this one away here. Less confused. This is this chi of W dot lambda plus. Okay, now since we're projecting onto the new block over here, then this W dot lambda plus nu has to be linked to so this is all nu in x of t such that lambda plus nu is linked to. Okay, so we get this nice formula, and we actually proved this last time. All right. Okay, so now I want to break down a technical lemma. So this is actually proved in Janssen's book in detail. Very technical. So I'd rather not, go over it in class, but let me just kind of give you a feel for what it really says. So suppose you take two weights which are in the closure of the bottom alcove. Okay? And let U1 be a dominant weight, which is conjugate to U minus lambda. Okay, so remember, this is the dominant weight you pick when you're doing translation from U to lambda. So part A says the following. So then, if I take lambda plus W times nu, this turns out to not be WP conjugate to mu under the following conditions. So for any W and W and U less than U1. Okay, so as long as my nu is less than nu1, and I take W conjugates of this weight, which is less than nu1, then lambda plus this thing is not WP conjugate under the dot action. Okay, so the only time this could actually happen is if you're looking at conjugates of nu1. Okay. And that's what I'm going to say next. It's kind of an amazing, when you think about it, it's kind of an amazing fact that you don't have to think about. So what are you really going to do when you translate? You're going to do something like this over here, and then this m is going to be m times m nu1, right? And so we're going to be able to apply this to this fact involving translation. So you can kind of see how this is sort of the translated module in some sense, and you have these conditions up here, and how this is going to be related. So you stare at it for a second. Okay, so the second thing is if W is in W, and I have lambda plus W U1, that can be conjugate in there. So if you have a situation where that is true, it can actually happen. Then there exists, let's see, some W1 and WP with, well, first of all, it's going to stabilize lambda. So it's kind of amazing. You have something which is going to stabilize lambda. And when you take this thing and you dot it times this, this will actually equal this one over here. Okay. So what we're saying is that if you have something which is conjugate to mu under the dot action over here, we can represent it in a way where this nu1 actually stabilizes lambda. Okay, you can actually pick a W1 which actually does this. All right, so then you sort of think, well, some alcove geometry is happening. Okay. All right, so again, this is a pretty technical lemma. It takes some work to actually prove this, but this is basically the only thing I'm not going to prove. Okay, any questions on this so far? Okay, so the next thing we're going to do is we're going to apply this calculation and take a module, let's say with this condition over here, And then we're going to take the translation functor, and we're going to actually calculate the character of the translation functor using this over here. All right. Any questions so far? Does everyone have this written down? All right. So the goal here is to find formula character of that. Okay. Actually, I want them reversed. It doesn't really matter, but for conventional reasons. Let me just reverse these. All right. Okay, so here's the proposition. So I don't know, maybe let me just, I think it's a great result actually. So this is a theorem. So this theorem was probably due, I think it's due to Janssen. So let lambda mu in CZ bar. Okay. V finite dimensional G module. Okay. With again PR lambda of V. So right. So let, okay, so we can write the character of V again in the way that we had in the previous result. So W and WP, AW chi of W dot. Okay, again, the AWs are integers and then it's a finite sum, right? Okay, so then, well, you think that if I like translate the module, then it's going to be some horrible formula. But it's not so bad. So then the character of the translated module, okay, so this is translated from lambda to mu of V is equal to the sum of W and WP of AW. Okay, the sum is now over W1, kind of suggestive of what I put in the technical lemma over here. Chi W W1 dot V. Okay. All right, this makes sense, right? Because I'm going from the lambda block over here to the mu block. So I better have things which are conjugate than the mu over here. Right? Okay, so we know where the A is coming from. We know where the W is coming from. And then I can tell you where W1 is coming from. So where W1 runs over system of coset representatives for following group. So, so W1 is going to come from the stabilizer of lambda. That's the first. So you want to take the stabilizer of WP of lambda. Okay. Now I need to factor this, and it turns out that you take all the ones out which actually have the same stabilizer underneath. So stabilizer WP of mu. Now these two could be like incompatible, right? So this better be a subgroup for this, so I'm just going to intersect it. So hopefully that makes sense. Okay, any questions on this?
Doesn't have to be normal, you're saying, just.
No, just, I mean, one's a subgroup inside the other. Just take cosine representatives. Okay. Good. Okay. All right, so now I am going to use the technical lemma, so I want to keep that up there. Does everyone have this part written down? You're going to have to refer to this. Right? So, okay, so let me do that. Okay, so let me erase this. All right, so let's prove this. Okay, so so what's the idea? So the character, I'm just going to write it out. Lambda mu of b, by definition, is the character of PR mu, L mu 1, tensor PR lambda b. Okay, so remember this is b here. Okay. All right. So now what we do is we use the prior result first. Okay, so by the prior result, we know what this is. This is the sum over W and WP, AW, summation of mu, dimension of L mu1 mu, chi of W dot lambda plus. Okay, so this is exactly what I had before. You want to write with that? So this is, remember, this is a prior formula. Well, that part's not being videotaped, so we can kind of keep that off to the side. All right, good. All right. Okay, so now what we do, so remember what this was too. We actually proved this before. So this is actually equal to W dot lambda plus 2. Okay, so we by sort of doing some sort of re-indexing, we can think of it that way too. All right. Okay, so that's where we get over into this case over here. So basically, first of all, we need, so what do we need? So we're projecting on the mu. So we need here that lambda plus nu is in WP dot lambda mu, right? Okay. Right, and remember here, this nu is less than nu1, because it's a weight, right? So we have the nu is less than or equal to nu1. Okay, so now we go over here, and we notice that whenever we take a nu less than nu1 in any W conjugate, then it's not inside of here, right? So basically, when you take your weights, let's say this is nu1, and you shell around, you're okay in this shell, but when you have a nu here, and you sort of shell around like this, all the weights in the W conjugate are not going to contribute to this because of it. All right? You want to go with that? Okay. So now I can rewrite this as summation W and WP of AW. Okay, so the thing is, we only have one over here, right? So remember, so let me just write this out. So these are all the conjugates where you're actually taking things inside of W orbital. All right, so how do I want to write this? You're going to have it over here someplace. All right, so let me rewrite this. So AW U and X of P. Let's see, which. Yeah, so let me think. Sorry, I got it down. Let me rewrite this. And then I'll explain, okay? So basically, let me rewrite this. So this is over W1 pi W of W1 dot one. All right. So first of all, by A, you can get rid of this in terms of, this will always be 1 because the only thing that's going to contribute here are the n's, which are equal or conjugate to nu 1. So note that the only contributions are when nu is in conjugate of nu 1, and in that case, the dimension of L nu 1 of nu is 1 dimension. Right? It's conjugate. We're sort of on the outer shell out here. Okay. All right. So then this nu is a conjugate of nu 1. So now you're in case B over here, right? You're in a conjugate of nu 1 over here. And it has to be inside of here. So there exists a W1 such that lambda plus W times nu 1 is equal to W1 mu. Okay, so we can actually replace this over here by this. Everyone okay with that? Okay, so we're using part A here and then part B. Okay. So this is by A and B. Of the technical one. Okay, now the only thing I have to do now is I have to justify, like, counting which new ones will actually, what I can quantify where the W1s are. Okay? So that's what we need to do next, and then we're done. Because that's the formula. Okay, so first of all, the W1s here that we represent this by are all in the stabilizer. Okay, so by B, we know that W1 here is in the stabilizer. Okay, so when we do the sum, we can always say that's inside the stabilizer. And so what are we going to mod out by? Well, we just don't want these things to duplicate themselves, right? Because we can get another W1, which possibly can be equal to this, right? So we don't want duplications. We don't want duplication. So we don't want so we can have this guy equal this guy equal to lambda plus W1. Right? So we can get different W1 and W2s, which actually equal this too, which are in the stabilizer. But then we want to, so these things will differ by the stabilizer mu. Right? Okay. So this implies that W1 is then W2 times the stabilizer of mu. Okay, so that we have to, in order to avoid duplications, we have to factor out. Okay. So running out of space. Because I think I've worked both of these already for you and shown you how this works. So therefore, let me just erase the whole thing. So therefore, take representatives in stabilizer WP lambda by stabilizer WP lambda intersection stabilizer WP. All right, any questions on this? Does this make sense? So it's kind of neat right here. I mean, it's kind of amazing that you don't have to take any news which are in the inner shell of your sort of weight diagram. You just have to consider the ones which are on the outer shell in this form by this technical. Okay, good. All right. So this formula will be incredibly useful. Now, what we're going to do next is we're going to kind of leave this formula for now, and we're going to apply it in a moment. But what we have to do first is we have to sort of talk about natural transformation. Okay, so let me give you a brief introduction. So how many people have actually seen the idea of natural transformations before? Okay, so how many people actually remember what natural transformations are? You want to say roughly what they are?
Is basically for each morphism in the category, you're getting commuting square.
Right, so yeah, so what you want is you take two functors and you sort of want to relate them in a certain way. Okay, that's what sort of natural transformations do. So let me give you the definition up here. And what we'll do is we'll actually use the translation functors to create a natural transformation to the identity functor. Okay. And once we do that, sort of both ways, both compositions, then that will give us the equivalence of categories. Right. Okay, so that's the idea. So let script C and script D, let them be categories. Right. And what we're going to do is we're going to let S be a functor from C to D, and T be a functor also from C to D. Okay, so these are the. Now you can do this with contravariant functors, but for the sake of simplicity, let's just stick with covariant functors, so they don't switch the arrows around. Okay? So these are covariant functors. Okay. So a natural transformation let's see, we'll call it alpha from S to T. So this is the notation for a natural transformation. is a function that assigns to each object, let's say, let's call this. So I'm going to make this a regular C, okay? So an object C in script C, a morphism. So this is a confusing part because it doesn't assign another object, it assigns it a morphism. Okay, so this is called alpha C, and it goes from applying the functor C on S, okay, to the functor T of C. Okay, and now here's where you get the commuting squares in such a way that for any function from C to C prime, we'll get the following square. So I have S of C up here, I have T of C over here, okay? So I have this natural transformation, alpha C. So I have this arrow, there's an alpha C over here, okay? Now, I have C prime down here too, and I have C prime over here. I could look at their images also. And I have a natural transformation for C prime also. So I have alpha and I have a C prime over here. Now, I need to get the F in the picture. So I have a map which goes from morphism, which goes from C to C prime. Well, this is the functor. So I have a morphism here, which is just given by S of F. And I have a morphism here, which is given by T of F. Okay. And so you want this to happen for every C and C prime. And that's a natural prime. That's a natural transformation. Okay. So this is a natural transformation. So if alpha C is an equivalence isomorphism for all C and script C, then alpha is called natural isomorphism. Okay. It's also called the equivalence of S and T. Right? Okay, so same thing as S and T are equivalent. Okay. Now, the categories C and D are equivalent. So script C, script D are equivalent. If and only if, when I take S composed with T, this is naturally isomorphic to the identity function, and then the same with T. Okay, so the natural equivalent, you can just compose the functors to get another contravariant functor, and I want there to be natural isomorphisms between this functor, identity functor, and this functor. Okay, any questions on this? All right, good. So now let's kind of bring this down to earth. So we have these translation functors, and now what we want to do is we want to produce equivalences of categories. Okay. All right, so I think we'll be able to prove this thorough. You know, chalk, let's see, can I get a long piece of chalk? All right, so here's the theorem. Okay, so suppose that lambda mu are again in the bottom of the book, and this and belong to same set. Okay, so they're basically, like the two of them could be on the interior, or they could be on the same wall, for example. So if they're on the same facet, the stabilizers are the same. The stabilizer of the affine Weil group on lambda is the same as the stabilizer of the affine Weil group. Okay, so that's an important thing because when I erase this off the board, then what does that say? Well, it says that there's only one element in the coset. Good. Okay. So then, when you have them on the same facet, P lambda mu induces equivalence of categories so I'll call this, I'll try to use the same notation over script C, which is G modules such that PR lambda V equals V. Okay. So basically modules where all the composition factors are linked to lambda. Okay. 2, script D, which is also G modules, such that PR mu of V. Okay. So the functor taking the composition in the lambda. So I take lambda. So I go from the lambda block to the mu block, then I go to the mu block to lambda block. So this is isomorphic. This is going to be equivalent to PR of lambda, which is on this category, just the identity. Okay. All right. So once I actually show all this, right, show that these functors here, this composition is naturally isomorphic to this, then we can say that these categories are equivalent. Okay, so let's set it up and let's prove it. And so the first, basically, first of all, employs the adjoinness, and then for each object, what we have to do is we have to show that the natural transformation actually is an equivalence. Okay. So let's do that. How are we doing? Okay, good. So by the adjoinness of P lambda mu and P mu lambda, we have the following. We have palm of G of V of C mu lambda mu of V. This is isomorphic with palm G. So I can just pull one of these off and sort of flip it and put it over here. So this is P lambda mu All right, so now what do you do? Well, so I'm going to let. So my F is my alpha here. So what do I want to do is I want to assign. So I want to show that these two are equivalent, right? So what I want to do is notice that this is set up over here. So what I do is I sort of start with a V, and I take the identity over here, and I push it using this isomorphism over here. Okay, and that's what I'm going to do. So this assignment. So what are we trying to do? We're trying to show this is our composition. So this is the S here, and this is the T in the over here. Okay. So what I need to do is I need to actually say where this goes to. Okay, so this is so this corresponds. To the identity out from E lambda mu of V. Okay, so for any morphism over here, I can actually for any object here, I go to here, I pick the identity out, and then I get a map from here to unique. Okay, is that clear how we did this? Okay. All right. So this actually forms a natural transformation. So we get a natural transformation. All right, so I can just go into the picture and you can just check that everything commutes. So let me put the picture up. So basically I have the V here, and then it goes to this thing. Okay. And I have a morphism, which can go from here, and then so I have a morphism that way. And so this is going to be F of V, and this is F of V prime. And this is just this is basically just the identity. Okay, so does everyone see that how this is kind of set up? Okay, so what do we have to do next? Well, we have to show that all of these horizontal arrows are equivalences or isomorphisms. Well, how are we going to do that? Well, we're just going to show the characters are the same. Okay, that means the dimensions of the modules are the same, and everything's good to go. Okay, so we need to show F of V is now, these are all maps of G modules. Right? So what you can do is you can assume V is simple first, right? And then you know it's not going to be the zero morphism. You show the characters are the same. It's not the zero morphism. It's going to have to be an isomorphism because these are maps of G modules. So notice like F of V are maps of G modules. Okay. So what you do is you show first that it works for irreducible modules. Okay. And then you just use induction on the composition length. Okay. the composition length. And then you could use like the 5 limit to actually do the whole thing. Okay, is that clear? Is that kind of clear how to do this? So once we actually do it here, then you could just use, the short exact sequence, and then you can just, you have isomorphisms going this way in 2 of the slots. And then so you have isomorphism. And then, so we use 5 or something. All right, so the main thing is to actually show it works for the simple modules. Okay, good. Now, we're not going to use anything about the simple modules in particular. We're just going to use we have the character formula on the translated models. Let's say B is simple. So now, what is the character? So let's look at the character of mu lambda, character lambda mu of V. Okay, so now I'm going to use the formula. So this is the sum W and WP of V dot V. Sum of W1 and W2 of chi of W of W2 W1 dot lambda. Okay, so you sort of apply this twice. Okay, that's the point. Okay, so this is by the previous one. Okay. Well, where's W1? Well, W1 is in the stabilizer. Mu factored out by the stabilizer lambda intersection of the stabilizer and mu. Okay, so that's what the total means, right? So what is W2? That's in the stabilizer lambda modulo some other stuff. Okay. Now, if these weights lambda and mu are in the same facet, the stabilizers are the same. So now, it's kind of the easy part. So, but lambda and mu are on the same facet. Okay, so let me just draw you a little picture here. So, for example, you can have lambda and mu over here, for example. Okay. So because they're on the same facet, the stabilizer is the same. The elements of the affine Weyl groups, which stabilizes the thing, is just the reflection across this hyperplane over here. Okay. Or on the other hand, you could have this on the interior, and the stabilizer are the same too. Okay. So W1 we can choose as being the identity, and W2 is the identity too, because these have this here in the squiggle is the same as the thing on the top. Okay, and similarly down here too. Okay. So if these two are the identity, product is the identity too, and then you just get the character of V back. Right? And so that's how you're using it. All right. Okay, so hence F of V after, so we did it for the simple modules here. So F of V is going to be equivalence by using induction on composition length for the 5 level. So this is an isomorphism all the time of G modules. Okay, so that means that basically the composition here, which way do they have it? So T lambda mu, T mu lambda is equivalent basically to PR lambda. Okay. Now, you just reverse this to show the other values. So similarly, T lambda mu composed with T mu lambda is also equivalent to PR. Okay, so when I restrict this down to those categories, these are the identity, and so therefore these two functors induce equivalence of categories. So I'll just write this down. So finally, proves that d lambda and d mu equivalent, where d lambda is a set of v such that er lambda v is v. So v is a G module. This actually works for any G module, so I'll just do infinite generate ones too. You can sort of jack this argument up if you do. All right, any questions on this? Okay, so we actually know what happens on, let's say, things with the same facet. All right, so you basically just have to take a representative of a block on a certain facet. Okay. So the next thing we're going to do is we're going to sort of explore what happens in modules when we translate like from an alcove to a wall and vice versa. So we know what happens when we translate from things on the same facet. We don't do anything, we just get equivalents of categories. So question. So what about translating from an alcove into a wall? So what happens in that case? Now, fortunately, the formula that I proved actually works in general. When you take a module, let's say it's a module like let's say here in this block, and we sort of translate it to this wall, well, we know what happens with the character. And the character will actually involve looking at stabilizers. So what we'll be able to show is that, like when I take an induced module, if I translate it to the wall, then it's going to be another induced module. Nothing more, or it'll be zero. It depends on whether the weight is dominant. So for example, if I take an induced module H0 lambda here, if I translate it here, I'm going to get zero. Because this wall is not dominant. Right? On the other hand, if I translate it up here, where this wall is dominant, then it will be another H0. Okay. And then you can actually ask yourself what happens when you translate off of walls, and that turns out to be more interesting. And that's actually related to what's called the Mystic conjecture. We'll sort of get into that later on. Okay, are there any questions on this, on these ideas? So, hopefully we've done a lot of the hard work in this session with, getting the character formula for the translation module. Once you have that, then you have a lot of, you can use that to get a lot of mileage. Okay, so let's stop here. We'll continue on Wednesday. Yeah.
The first time I've seen somebody actually define equivalence of categories.
Okay, I mean,
See, it's one of those things you see everywhere, but like nobody ever writes it down.
well,